Okay, so now let's use the definition that we had for basically theoretical probability to solve some problems. Now, what we want to do here, we want to find the probability for some of the events associated with experiments where the equally likely assumption holds. So this is important. We want to find the probability for some events associated with experiments where the equally likely assumption holds. So this is important, otherwise you wouldn't be able to use the basically you wouldn't be able to use this concept for the kind of experiments where the equally likely assumption does not hold. There, of course, you cannot, I mean, logically you cannot use it. So, for example, as an example, you want to find basically the probability of getting a head when the coin is tossed once. Also find the probability of getting a tail. So you basically toss a coin, and then you want to find the probability of getting a head, of getting basically a heads, and you want to find the probability of getting a tails, right? So if I assume that that basically tails and heads are equally likely in this experiment, then I can use, for example, the definition that we had. For example, I can write P of E, which is P of, for example, which I could write as P of heads. P of heads would be equal to basically the number of outcomes favorable to the number of outcomes favorable to E, the number of outcomes favorable to E. And of course my handwriting is not that bad, but the pen is playing up kind of. I need to restart my computer after this video. So you have the number of outcomes favorable to E divided by the number of all possible outcomes. Divided by the number of all possible outcomes of the experiment, which is equal to 1 divided by 2. And similarly, you can say that, for example, P of F, for example, I can define P of F as, for example, P of tails. I can basically write that as the number of outcomes favorable to F, which is 1, again to the number of all possible outcomes, which is 2, which is basically tails and heads. And let me go back to the definition that we had over here. We said that the theoretical probability, the theoretical probability of, also called the classical probability of an event E, written as basically P of E, is defined as P of E. So this is the theoretical probability of an event E, is basically defined as the number of outcomes favorable to E, the number of outcomes favorable to E divided by the number of all possible outcomes of the experiment. The number of all possible outcomes of the experiment. So that's basically the theoretical probability of an event E. We said that it's the number of outcomes favorable to E to the number of all possible outcomes of the experiment, which is, for example, in the case of tossing a coin, the number of, for example, if I'm talking about the probability of getting heads, for example, so the number of outcomes favorable to E would be just 1, because heads can happen only in one way, so that would be a 1. And the number of all possible outcomes of the experiment would be 2, because you could get either heads or tails. So then, for example, in that case, P of E would be equal to 1 divided by 2. And the same goes for example, P of tails, for example. Now, let's say that you have, for example, a bag contains a red ball, a blue ball, and a yellow ball, all the balls being of the same size. So you have a bag, it contains a red ball, so you have a red ball. So you have one of these red balls, you have a blue ball. So you have a blue ball, one of these, and you have a yellow ball as well. Right? And all of these are of the same size. Now, Kritika, which is a name, takes out the ball from the bag without looking into it. What is the probability that she takes out the yellow ball or the red ball or the blue ball? So, the probability that she takes the yellow ball, from now on I'm going to write probability as PROB. Probability that she takes the yellow ball is basically, let's call it P of E1, for example. That would be basically all the number of outcomes favorable to E, which is basically in this case is equal to 1, and all the number of possible outcomes of the experiment, which is basically 3, because you could take out the red ball, you could take out the blue ball, and you could take out the yellow ball. So the probability that she takes the yellow ball, she takes out the yellow ball without looking into the bag, is 1/3. Now, the probability that she takes out the she takes out for example, the red ball is basically, if I call it P of E2, that would be again equal to 1/3, because the number of outcomes favorable to that event happening is just 1, because there is only one red ball in the bag. And but of course this number changes, because then there is only 2 balls left in the bag. Now I don't know how they have solved this problem. This is assuming that still there is, for example, when you calculate the probability that she takes out the red ball, still that's going to be equal to 1/3, because I'm assuming that I have not taken out the yellow one. So that's still going to be equal to 1/3. And the probability that she takes out the basically here I have the yellow ball, the red ball, and the blue ball. The probability that she takes out the blue ball, that would still be equal to 1/3. If I call it, for example, P of E3, that would still be equal to 1/3, because the number of outcomes favorable to E, or basically in this case E3, would be equal to 1, because there is only one blue ball in the bag, and there is a total number of 3 balls in the bag. So then again you will end up with 1/3. So then all the probabilities would be 1/3, but then there is the problem that if you, for example, if you take out the yellow ball, then the number of balls remaining in the bag would become 2. So then this would be, for example, 1/2. And if you took this one out, then the probability of getting this ball would be 1 divided by 1, which is equal to 1, which is, you are definitely going to get it. So, but here we are assuming that we are just calculating the probability of getting this ball or that ball or that ball, and we are assuming that we are not actually taking the ball out. The ball remains in the bag. And as a remark, what we have here is an event having only one outcome of the experiment is called an elementary event. In example number 1, both the events E and F are elementary events. Similarly, in example number 2, all the 3 events are elementary events. And remark number 2, in example number 1, we note that P of E plus P of F is equal to 1. And in example number 2, we note that basically the probability of the three different possibilities was equal to 1. And so observe that the sum of the probabilities of all the elementary events of an experiment is equal to 1, and this is true in general also. So what that means is that an event having only one outcome, having only one outcome of the experiment is called an elementary event. So an elementary event is basically, for example, if you want to think of this in this case, for example, you have only one red ball in the bag. You have only one blue ball in the bag. You have only one yellow ball in the bag. And the probability And so the event of, for example, getting a red ball out of the bag, the event of drawing for example, a red ball from the bag, is the event of drawing a red ball from the bag is called an elementary event. Is called an elementary event because because the event has only one outcome of the experiment. Because the event has only one outcome of the experiment. So what that means is that, for example, right now we are talking about the red ball, right? And the situation was that basically there was only red ball in the bag. And so what that means is that the event of drawing a red ball from the bag is which is called basically an elementary event. That is because the event has only one outcome of the experiment, meaning that there is only one red ball in the bag. And so that's basically the definition of an elementary event. So now in this experiment, you can see that, for example, you can think of basically the event of taking a yellow ball as an, you can think of this event as an elementary basically as an elementary event. You can think of taking out the red ball as an elementary event. You can think of taking out the blue ball as an elementary event as well. And the reason is that basically this for example, this event has only one outcome of the experiment. And as you can see over here, the probability becomes 1 divided 1/3. This becomes 1/3, and this becomes 1/3 as well. So each of these events are elementary events. Now, P of E1, as you can see, P of E1, P of E2, P of E3, if you add them all together, P of E1 plus P of E2 plus P of E3, if you add them together, you'll get 1/3 plus 1/3 plus 1/3, which is equal to 3/3, which is equal to 1. Which means that the sum of the probabilities, of all the elementary events, of an experiment is 1. And this is in general true for any sort of experiment, because because that's basically what happens all the time. So this is true for any experiment in general. Now, okay, so now as another example, we have basically, suppose we throw a dice once. So we throw a dice once, and what is the probability of getting a number greater than 4? The probability of getting a number greater than 4, for example. Greater than 4. So to calculate that, so we said that basically we had basically the number of outcomes favorable to E, for example, if the event that we are looking at is E, divided by the number of all the possible outcomes of the experiment. Now, all the possible outcomes of this experiment throwing a dice would be 1, 2, 3, 4, 5, and 6. So there is 6 possible outcomes. And basically the outcomes favorable to this event happening, which is getting a number greater than 4, is basically 5 and 6. So you have basically 2 outcomes that are favorable to this event. So then you can say that, for example, if I call that P of E, then P of E would be equal to, for example, 2 divided by 6, which is equal to 1/3. So that is 1/3. And the second part of this question, what is the probability of getting a number less than or equal to 4? So what is the probability of a number of getting a number less than or equal to 4? So for example, P of F would be, the event is getting a number less than or equal to 4. So that would be less than or equal to 4. So that would be basically 4, 3, 2, and 1. So the number of those numbers is 4. You have 4 numbers over there. So that means that there are 4 events favorable to this. There are 4 events favorable to this event. And then you have basically the total number of all possible outcomes of the experiment is basically 6 here. So that's 4, 6, which is equal to 2/3. So are the events E and F in the example above elementary events? Of course they're not elementary events, because for example the probability of this event is 1/3. If basically you find the probability of some event related to this experiment, and if the probability is equal to basically 1/6, then in that case 6 is the number of all possible outcomes of the experiment. And 1 is just basically, this is only one possible experiment, only one possible outcome, only one possible outcome. And if that's the case, then that event is called an elementary event. So if P of, for example, E, for example, is equal to 1/6, then you can say then E is called an elementary event, right? Otherwise not. So none of these is an elementary event, because the event E has 2 outcomes and the event F has 4 outcomes. 2 outcomes and 4, and then you can see over here the event E has basically 2 outcomes here out of the total number of possible outcomes of the experiment, and the event F has 4 outcomes out of all the possible outcomes of the experiment. So that's 2 and 4. Okay, so now I said something about an event, and then I said that, for example, an event E, and then I pointed out to not E, which is of course used in mathematical logic, but it seems that what I said was actually not used exactly in this way here, and the concept was not really fitting here. And of course, what I said was not factually wrong, but and again, I did remember something from the concept here that I had read a long time ago, and well, it should be actually stated this way. Okay, now there is a fact that, I mean, basically in probability, you can say that the probability of an event and basically the sum of, you can say that, let me write this again. Well, what I mean to say is that the sum of the probabilities of an event and the probability of the complement of that event is always equal to 1. So the idea is, and of course I'm going to explain what I mean, the sum of the probabilities of an event related to some experiment and the complement of that same event is always equal to 1. So what that means, in simple words and in the form of an example, so we said that when you throw a dice, the only possible outcomes of this experiment, take this as an experiment, the only possible outcomes of this experiment would be these numbers: 1, 2, 3, 4, 5, and 6. These are all the possible outcomes of this experiment. Now I can, using these possible outcomes, of course you can define any sort of event that you wish. Meaning that, for example, I can basically define an event, for example, E1, and call it, for example, the event that the event of, for example, getting all the numbers greater than 4, greater than 4. And I could also say the event, for example, E2, and I can define it as the event of getting all the numbers less than or equal to 4. Or I can say that, for example, the event of getting not, there is a not over here, not all the numbers greater than 4. Now you can see that over here, basically event E1, the event of getting all the numbers greater than 4, would be basically getting these two numbers, 5 and 6. The event of getting not all the numbers greater than 4 would be basically these numbers here. So that would be, for example, event E2, for example. The event E2 would be the event of getting not all the numbers greater than 4. That would be basically getting all these numbers here. So I can rewrite this event E2 as the event of getting all the numbers less than or equal to 4. And now, so this is going to be, and of course this event would refer to basically these 4 numbers here. E2 refers to these 4 numbers here, and E1 basically refers to these 2 numbers over here. Now if I find the probability of the event E1, P of E1, that would be equal to 2 divided by 6, because you have basically two outcomes favorable to E1, and the total number of outcomes here is equal to 6, so that's 2 divided by 6, which is equal to 1/3. On the other hand, P of E2, if I calculate it, that would give me basically 4 divided by 6, meaning that the number of outcomes favorable to E2 would be this one event, another event, another event, and another event. That would be 4 events divided by the total number of possible outcomes of this experiment, which is 6, which is equal to 2/3. Now as you can see, P of E1 plus P of E2 is equal to 1/3 plus 2/3, which is equal to 3/3, which is equal to 1. So what that means is that, and of course, and in this situation, I can call E2, the event E2, I can call it the complement of event E1. I can call this event the complement of E1. The reason why I can do that is that basically, as you can see, related to event E2, I would get these two numbers 5 and 6, and as far as the event E2 is concerned, then I would get none of these numbers, and all the other numbers among all the possible basically outcomes of this experiment. So based on that, I can call basically the event E2 the complement of the event E1, and And moreover, I can call these two events, I can call the event E1 and E2 complementary events. And complementary events. I can call these complementary events because this is the complement of that one, this one is the complement of the other one. We also say that basically we also say that E1 and E2 if I denote E1, for example, by E, then E2 becomes the complement of E, which is denoted by basically E bar. So that means that since these two events are complementary events, if I denote E1, for example, by E, then E2 would be denoted by the complement of E, or E bar, which is basically the same thing, right? Now, and you know that, and then you can say in general that P of E plus P of E bar, or the complement, meaning that the probability of the event E plus the probability of the complement of E is equal to 1. That's basically the whole story here. But then of course you need to understand what it means to be, what it means for an event to be the complement of another event. And so now, before proceeding further, let us try to find the answers to the following questions. Now, for example, what is the probability of getting a number 8 in a single throw of a dice? What is the probability of getting an 8 in a single throw of a dice? In a single throw of a dice. So now, in order to answer this question, of course, you know that all the possible outcomes of throwing a dice would be 1, 2, 3, 4, 5, and 6. You could get any of these 6 numbers. And among these 6 possible outcomes, the number of outcomes favorable to this event happening, getting an 8, is basically, if I call this P of E, for example, the number of possible outcomes favorable to this event happening would be 0, because there is no way that this can happen. And the whole possible, basically the total number of possible outcomes of this experiment is 6. That is equal to 0. That means that this event basically cannot happen. And what is the probability of getting a number less than 7 in a single throw of a dice? What is the probability of getting a number less than 7? Getting a number less than 7 in a single throw of a dice. So again, if I call this, for example, P of E, all the possible outcomes of this experiment would be, the number of them would be 6. And all of these numbers are, of course, less than 7. So you have basically 6 possible outcomes. 6 possible outcomes favorable to this event of getting a number less than 7. So that would be 6, so that would be 1. And again, 1 plus 0, as you can see, is equal to 1. So So as the answer, it says that we know that there are only 6 possible outcomes in a single throw of a dice. These outcomes are 1, 2, 3 through 6. Since no face of a dice is marked as 8, so there is no outcome favorable to an 8 over here. That is, the number of such outcomes is 0. In other words, getting 8 in a single throw of a dice is impossible. This means that it is impossible. It is impossible. That means that P of getting an 8 is 0 divided by 6, which is equal to 0. And that is the probability of an event which is impossible is the probability of an event which is impossible to occur is 0, which we all understand. Such an event is called an impossible event. So this is called an impossible event, and it is actually a part of the terminology of probability. An impossible event, meaning that the probability of that event happening is 0. Moreover, part 2 of this question, since every face of a dice, the solution is, since every face of a dice is marked with a number less than 7, it is sure that we will always get a number less than 7 when it is thrown once. So the number of favorable outcomes is the same as the number of all possible outcomes, which is 6. That means that P of E is equal to 6 divided by 6, which is equal to 1. So the probability of an event which is sure or certain to occur is 1. Such an event is called a sure event or a certain event. So this is called a sure event, the sure event or a certain event. So basically we have now we have introduced 2 terminologies here. One is the impossible event. One is an impossible event, and one is a sure or certain event. And the definition for this is that if the probability of an event which is impossible to occur is 0, such an event is called an impossible event. And also the probability of an event which is sure or certain to happen is which is sure or certain to occur is 1. And so here you would get the P of E is equal to 0, and over here P of E is equal to 1. And such an event is called a sure event or a certain event. And also, as a note, we have from the definition of the probability P of E, we see that the numerator, or the number of outcomes favorable to the event E, is always less than or equal to the denominator, or the number of all possible outcomes. Meaning that these two numbers, the numerator over here is always less than or equal to the denominator, because you could not have more outcomes favorable to the event E. We could not have more events than the more events which are basically favorable to the event E than the total number of outcomes of the possible outcomes of the experiment. That means that P of E, since if I write, for example, P of E is equal to, if I call it A by B, and since A is always less than or equal to B, then that means that P of E is going to be some value greater than or equal to 0 and less than or equal to 1, but it cannot be greater than 1. Now let us now, so that cannot be greater than 1 and cannot be a negative number, of course. So let's take an example related to playing cards. Have you seen a deck of playing cards? It consists of 52 cards which are divided into 4 suits, 13 cards each. Spades, hearts, diamonds, and clubs. Clubs and spades are of black color, while hearts and diamonds are of the red color, and the cards in each suit are ace, king, queen, jack, 10, 9, 8 through 2. And then we have also the 1, which is the ace, of course. And king, queen, and jacks are called face cards. Okay, so in case you're like me, I've never actually played cards in my whole life, except for just a few times, in which case I've always lost the game, because I've never actually understood why do you even have to play that game, because it's a game, and well, of course, even if you win, there is no point, because that it was a game, and you have basically just, the only thing that has happened is that you have won a game, and winning a game is not in any way in any way valuable. So that's why I never played cards or any other games for that matter. And so I'm not really familiar with all kinds of games played with cards. And before I started basically studying mathematics, I even knew nothing about the names of these cards, which, like, for example, the spades, hearts, and diamonds, and clubs, and so on and so forth. But then when you come to any sort of mathematics books, all of these are all over the place, so you have to learn them. Now, in case you're anything like me and you don't know basically how these cards are organized, you have basically, in total, you have 52 cards. You have 52 cards here. And these 52 cards are divided into 4 suits. These are divided into 52 suits. Actually, this is supposed to be divided into 54 suits, and then of 13 cards each, of 13 cards each. Okay, and then these not 52 suits, but I'm sorry, 4 suits of 50. This is 4 suits of, you have 4 suits of basically 13 cards each, meaning 4 times 13 is equal to 52. And the name of the 4 suits are basically, the names are spades. The names are spades, hearts. There is basically diamonds, and there is the clubs. Now the spades is something like this. So if I were to draw it, it would look something like this. So it's basically something like this. This is, well, let me show you basically the spades and everything, because I don't want to be wasting your time, wasting my time. So the clubs are, these are black. These are black. The diamond is basically red. This is red. The hearts, of course, red, and the spades are black, right? And in order to see what they look like, of course, I'm sure you already have seen all of these. Everybody is familiar with these, except for me, especially apparently. But the four suits in playing cards are basically these. So these are basically the four ones that the four suits that we talked about. This is called the diamonds, this is called the clubs, these are called the clubs, these are called the hearts, and these are called the spades, right? Now, what happens is that the cards in each suit, in each suit, what you have in each suit, basically you have these cards in the order or in the hierarchy of the cards, meaning that, for example, first you have the ace, which is the highest card in that suit. In every suit you have basically these I would say denominations. You have the ace, then you have the king, then you have the queen, then you have the queen, then you have the jack, then you have 10, then you have 9, 8, 7, 6, 5, 4, and 3, and 2. So ace is actually 1, but it's been given the highest, basically the highest value in that hierarchy. Then there is the king, there is the queen, there is the jack, then 10, 9, 8, 7, 6, 5, 4, 3, 2. That's basically how these cards are organized. And the king, the ace, and the jack are called the face cards. Okay. Now, knowing all of this about how all of these 52 cards are organized, let's go and solve a couple of problems here. Okay, so example number 4 is one card is drawn from a well-shuffled deck of 52 cards. So you have a well-shuffled deck of 52 cards, and one card is drawn. One card is drawn at random. One card is drawn at random. Calculate the probability that the card will be. Calculate the probability that the card will be an ace, number 1, an ace, and number 2, and not be an ace, not an ace. Okay, so basically, so if I want to the first part, that if you want to calculate the first part, but we have a well shuffled deck of 52 cards and one card is drawn at random. Now we want to calculate the probability that the card will be an ace. So we said that if take this as, for example, event E1, and if I take this as event E2, the probability of event E1 happening is equal to basically all the outcomes favorable to E1, which is basically, since we have 4 aces in total in a deck of 52 cards, so I have basically I have 4 events favorable to, or I have 4 outcomes favorable to this event. So so my numerator becomes a 4. And then all the possible outcomes of the experiment is basically 52, because I have 52 cards in a deck. And so what that means is that you have 4 to 52, which is 2 to 26, 2 to 26, which is equal to 1/13. So 1 to 13 is equal to something like, for example, 10, that's 0. That is 1 to 13 is equal to basically 0.0, so then 0, and then if I have a 13, that would be 7 times 70 and 21. 7 times 13, because 7 times is equal to 21, 2, and 91. It's an 8 remainder, and then 80 would be 6, 18, no, 5. So that's the same thing as 0.08. Take this as 0.08. That means that the possibility or the probability of getting an ace is only a tiny 8%, right? And of course the probability 2, the part 2 of the question, if I call that event E2, then P of E2 can be calculated as basically, if the card is supposed to be not an ace, it could be any card other than the 4 aces that I have. So I have 4 aces there, and the total number of cards that I have is 52. So 52 minus 4 is going to be equal to 4 and 12, and then that's an 8, 48. So there are 48 cards that are not aces, which is basically the number of outcomes favorable to this event E2 happening. So I can write 48 divided by, and the total number of outcomes, possible outcomes of this experiment is 52, because I have 52 cards. And so that is equal to divide by 224, divide by 225, 26, divide by 212, divide by 213. So that's 12/13, something about 0.9, I suppose. 12/13. So you have 0 and then 0 over here. So I have 120. 5, 6, 7 times, that's 70 and 21, 8, 9 times would be 90, and 27, 90 and 30 is equal to 120. So I think 9 times would be 9 times is equal to 27, 2, 9, 11, 117, 3 remainder, 0, 0, and then 2 times, for example, 3 times 13 is equal to 39. 2 times 13 is equal to 2 times 13 is equal to 26, 4 remainder, and then you have a 0, 0 here, 3 times, so that would be 0.92. That would be 0.92. And let me divide these two numbers. There might be some problem here. 4 divided by 52 is equal to 0.76 or 0.076 or 0.08, which actually makes sense, because if you basically add 0.08 to 0.92, what you will get is basically that's a 1. That is a 1. And that is a 1 because these two events are complementary events. When you say that, when you want to calculate the probability that the card will be an ace, and then when you say that the card will not be an ace, then of course these two are complementary events. And of course, about two complementary events, you can say P of E1, as we discussed before. P of E1 plus P of E2 is equal to 1. That means that it was actually enough to calculate P of E1, and then based on that you could have calculated P of E2. Meaning that if I calculate P of E1 as 0.08, so I write P of E1, which is 0.08, 0.08 plus P of E2 is equal to 1. That means that P of E2 is equal to 1 minus 0.08. So 1 minus 0.08 is equal to 0.92. So P of E2 is equal to 0.92. So wherever you see complementary events, this relationship exists between complementary events. Now we have another question here. Let me see how many questions we have left here. And then 7, 8, 9, 10, 11, 12, 13. Okay, so it seems that okay, so what I will do now is end this video here, and then we have a couple more questions here to answer, and so I will see you in the next video.